Hello, everyone. My name is Zeyu Xiong, and today I'm going to talk about digital rock physics, an FFT-based method for permeability and formation factor of sandstone. Permeability and formation factor are two important parameters of porous media. Conventional rock physics computes the two parameters based on the empirical relations or idealized models, which is oversimplified regarding pore geometry. Digital rock physics based on micro-CT images, however, enables us to simulate for the two parameters with complex pore geometry, which is more accurate than conventional rock physics. Popular numerical algorithms for digital rock physics include finite difference, finite element method, or Lattice-Boltzmann method. In this presentation, we will focus on the FFT-based simulation method because it is a computationally efficient, mesh-free algorithm, and it naturally imposes the periodic boundary conditions for porous media. In the rest of the presentation, I will talk about processing micro-CT images with interfacial treatment, solving two differential equations with FFT-based method for permeability and formation factor, and finally, the validation against the experimental measurements. The original data is a 3D micro-CT image originated from a cylindrical-shaped Beira sandstone sample provided by our collaborator, Dr. Wang. The RVE samples are generated by cropping a cube from the original data, coarsened to reduce the computational cost, and then binarized to separate the fluid and solid phases. To compute the permeability, the viscosity field is needed to solve the Stokes equation, where solid has infinite viscosity and the fluid has constant viscosity. In addition, the interfacial region with intermediate viscosity is introduced to impose slip condition. Unlike previous work, which generated the interface with finite thickness, we determine the interfacial viscosity based on the brightness of the grayscale image between the two tolerance values. In addition to permeability, the formation factor is also an important parameter. To compute the formation factor, the conductivity field is needed to solve the charge conservation equation, where both solid and fluid have isotropic conductivity. Additionally, the interfacial conductivity should be treated differently because there physically exists a thin layer of surface conductivity. Different from previous work, which treated the interfacial conductivity as a scalar, we computed the conductivity as a tensor that consists of normal and tangential components, with the unit normal vectors computed from the gradient of sign distance function. After processing the micro-CT images, we can calculate the permeability with the FFT-based method. Suppose that we have an RVE made of solid and liquid phases. Upon the external pressure gradient, the fluid will flow through the void with local velocity v, which is simulated by solving the Stokes equation with FFT-based method. And the permeability tensor relates the global pressure gradient to the homogenized fluid velocity. The Stokes equation is rewritten into the Lippmann-Schwinger equation in stress space, where the green operator gamma enforces the stress equilibrium and the strain compatibility during the conjugate gradient iteration, and the compliance tensor M enforces the incompressibility of the liquid and the zero velocity of the solid. Similarly, we obtain the formation factor by solving the charge conservation equation with the FFT-based method. By applying the electrostatic potential gradient over this porous media, the local current density is simulated by solving the charge conservation equation, which is equivalently rewritten into the Liebman-Schwinger equation with the electrostatic potential gradient as the unknown field. The green operator ensures the current field to be divergence-free and the potential gradient to be curl-free, while the conductivity tensor A is anisotropic within the surface layer. Here, we verify the permeability calculation against the analytical solution and lattice-Boltzmann method. For a 2D problem with fluid flow around the solid circle, the FFT-based method can solve the desired velocity field and permeability with different circle radius. We further compared FFT-based method with lattice-Boltzmann method using a 3D piled ball structure. Again, we get comparable velocity field, which verifies our FFT-based method. Here, we want to emphasize that the solid viscosity was said to be 100 times larger than the viscosity of the fluid. We later did a convergence study and found that the permeability tensor converges when the solid viscosity is 10 million times larger than the fluid viscosity. To compute the permeability tensor, we first solved for the velocity field by applying a pressure gradient in EI direction. Then homogenized the velocity field and finally computed each component of the permeability tensor from the homogenized velocity. Similarly, the effective conductivity tensor is computed from the homogenized current under a uniaxial potential gradient, and the formation factor is based on the inverse of the effective conductivity. Under the uniaxial pressure or potential gradient, the velocity and current field can be visualized by streamline contours. The streamlines are localized in a few flow paths instead of distributing in the entire pole space. However, to homogenize the velocity and current field, we should take into account the flow field in the entire RVE domain. The eigenvalues of the permeability and formation factor are studied and compared to the experimental measurements. Most of our results fall into the confidence interval from the literature, and the outlier results are mostly the least eigenvalues of the permeability, which tend to be underestimated. We also found that without interfacial treatment, the permeability results can be affected by several orders of magnitude. In summary, we propose a procedure to compute the permeability and formation factor based on micro-CT images. We introduced the interfacial treatment for image processing, solved for local velocity and current field with FFT-based method, and homogenized velocity and current for permeability and formation factor. By comparing our results with experimental measurements, most of our results fall into the confidence interval, except for the least eigenvalues of the permeability, which tend to be underestimated. The future work will be the geometric learning for permeability and formation factor prediction based on our results from the FFT-based method. At the end of the presentation, I would like to acknowledge our sponsors for supporting our research. And thank you very much for listening.